Introduction. Tanuj, what are you doing? I'm searching one of the science educational DVD. Can you please help me in finding the DVD? Sure. Amit, can you please tell me something? Yeah, definitely. Why is this DVD shining in a rainbow pattern? What's the reason behind this colorful shine? Okay, I will tell you. It happens due to the diffraction of waves. Diffraction occurs when the wavelength of the wave are in order of the object size. The closely spaced tracks on the DVD are comparable with the wavelength of wave. That's why we observe the colorful shine of DVD. Okay, I got it. It's quite an interesting fact. Can you please tell me something more about this? I'm curious to know. Okay, let's today study more about the wave optics. Objectives. At the end of this lesson, you will be able to define diffraction, understand diffraction due to a single slit, differentiate between interference and diffraction, define resolving power, calculate resolving power of a microscope and telescope, define polarization and Polaroids, understand Malus law, describe polarization by scattering, reflection and refraction. Diffraction. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. Diffraction is of two types: Fresnel's diffraction and Fraunhofer's diffraction. In Fresnel's diffraction, source and screen are close to the obstacle and light after diffraction appears converging towards the screen and hence no lens is required to observe it. In Fraunhofer's class, source and screen are at large distance from the obstacle. A converging lens is used to observe it. Diffraction due to a single slit. Consider a plane wavefront incident on the slit AB. Each point of the incident wavefront will be a source of secondary wavelets. These wavelets emanate from the wavefront in the same phase. To understand the formation of central maximum, the slit can be imagined to be divided into a number of very narrow strips of equal width parallel to the slit. All the wavelets originate from the narrow strip in the same phase. All these wavelets arrive at O in the same phase. These wavelets reinforce each other's effect to give maximum intensity at O. Now consider the formation of secondary minima and secondary maxima. Secondary wavelets diffracted at angle theta reaching a general point P on the screen. The wavelets shall not arrive at P in the same phase because these cover unequal distances in reaching P. Path difference between the extreme wavelets is given by Bn is equal to d sine theta. The condition for first secondary maximum is given at angle equals to 3 lambda upon 2d. The condition for second secondary maximum is given at an angle equals to 5 lambda upon 2d. Hence, the condition for nth maximum is given at an angle equals to 2n plus 1 lambda upon 2d. Width of secondary maximum is given by beta is equal to d lambda upon small d. Width of central maximum is given by beta naught is equal to 2d lambda upon small d. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. Example: Let's take an example on diffraction pattern due to single slit. Determine the angular spread between central maximum and first order maximum of the diffraction pattern due to a single slit of width 0.25 mm when light of wavelength 5890 Armstrong is incident on it normally. Let's see the solution. We know that half the angular spread is given by a sin theta is equal to 2n plus 1 lambda by 2. On equating this, we get lambda by 2 is equal to 3 lambda by 2. When theta is small, then value of sin theta is equivalent to theta. It gives a theta is equal to 3 lambda by 2. On putting the values, we get the value of theta is equal to 3.530 multiplied by 10 raised to the power minus 3. Hence, the total angular spread is equal to 3.530 multiplied by 10 raised to the power minus 3 radians. Difference between interference and diffraction. Interference is the result of superposition of waves starting from two different wavefronts, whereas diffraction is the result of superposition of waves starting from different portions of the same wavefront. All bright fringes in an interference pattern are of same intensity, whereas intensity of brightness in a diffraction pattern decreases as one moves away from the central bright fringe. The points of minimum intensity in an interference pattern are perfectly dark, whereas the points of minimum intensity are not perfectly dark in a diffraction pattern. Resolving power. The ability of an optical instrument to produce separate images of two objects very close together is called resolving power. Rayleigh criteria. When the central maximum in the diffraction pattern of one point source falls over the first minimum in the diffraction pattern of the other point source, then the 2 point sources are said to have been resolved by the optical instrument. Resolving power of a lens. The resolving power of a lens is its ability to resolve 2 points that are close to each other. The resolving power is directly proportional to the aperture of the lens and inversely proportional to the wavelength of light used. Resolving power of a microscope. The resolving power of a microscope is defined as the reciprocal of the distance between two objects which can be just resolved when seen through the microscope. 1 upon delta D is equal to 2 mu sin theta upon lambda, where lambda is the wavelength of light, mu is the refractive index of the medium, and theta is the half angle of the cone of light from the point object. The term mu sin theta is called the numerical aperture of the objective. To increase the resolving power of a microscope, mu is increased by using suitable oil between the object and the objective. Resolving power of a telescope. Point-like sources separated by an angle smaller than the angular resolution cannot be resolved. A single optical telescope may have an angular resolution less than 1 arc second. The angular resolution of a telescope is given by R is equal to lambda divided by D, where lambda is the wavelength of the observed radiation and D is the diameter of the telescope's objective. Resulting R is in radians. Sources larger than the angular resolution are called extended sources and smaller sources are called point sources. The resolving power of a telescope is the reciprocal of the smallest angular separation between two distant objects whose images are separated in the telescope. d theta is equal to 1.22 lambda divided by A. A telescope with a larger aperture objective gives a high resolving power. Polarization. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Plane polarized light is the light in which the vibrations of light are confined in a particular plane. Plane of vibration is the plane which is perpendicular to the plane of vibration. Polarizing angle is that angle of incidence at which the reflected light is completely plane polarized. Polaroids. Polaroid is a type of plastic sheet that can polarize a transmitted beam of normal light because it is composed of long parallel molecules. It only transmits plane polarized light if these molecules are parallel to the plane of polarization. Since reflected light is partly polarized, it is often used in sunglasses to eliminate glare. Linearly polarized light can be produced from unpolarized light with the help of Polaroid. The direction of polarization that a polarizing material allows through is called the transmission axis. Uses of Polaroids. Some important uses of Polaroids are following. It is used to avoid the glare of light. If we use sunglasses fitted with Polaroid, the eyes will not experience any glare. Polaroid sheets are fitted in car headlights and windscreen to avoid glare. Two Polaroid sheets are put one behind the other to control the light in window of aeroplane and big hotels. Camera used to photograph the clouds is fitted with Polaroid before the camera lens. Properly designed Polaroid glasses are used to produce and view a three-dimensional image. They are also used for studying optical properties of metals.
Malice's law. According to Malice's law, when completely plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axes of the analyzer and the polarizer. Suppose that theta is the angle between the transmission directions of the polarizer and analyzer. The intensity of the light transmitted by the analyzer varies with theta according to I equals I naught cos square theta, where I naught is the intensity of the light entering the analyzer.
Polarization by scattering. Consider an unpolarized light traveling along the y-axis strikes a gas atom at A. The electrons in the atom are set into oscillation in the xz plane by the oscillating E field of the incident wave. The radiation reaching O would come entirely from the dipole at A oscillating in the z direction and would be linearly polarized in the z direction. The transmitted radiation along y-axis is unpolarized because both dipoles can radiate equally well in the y direction. Sunlight scattered off atoms or molecules in the atmosphere of the Earth may also be polarized. If the atmosphere were not there, the sky would appear black except in the direction of the sun. Polarization by reflection. When light falls on the interface between two transparent media, it is partially reflected and partially refracted. The amount of light reflected or refracted depends on the polarization of the light relative to the interface. Consider an unpolarized light striking the interface between medium 1 and medium 2. At one particular angle, no light with polarization in the plane of incidence is reflected. All the reflected light is linearly polarized perpendicular to the plane of incidence. This angle of incidence is called the polarizing angle. Tan IP is equal to N, where N is the refractive index of the medium on which the light is incident. This equation is known as Brewster's law. Polarization by refraction. When ordinary light is incident on a glass plate at polarizing angle, the reflected light is plane polarized while the refracted component is partially polarized. Now, if this refracted beam is made to strike another glass plate at the polarizing angle, the same thing will be repeated at both the surfaces of glass plate. If the process is repeated using a number of parallel faced glass plates and light is incident on it at polarizing angle, then the beam emerging after refraction through these large number of plates will have almost all vibrations lying in the plane of incidence. The transmitted beam is thus plane polarized with vibrations in the plane of incidence. Did you know? Diffraction grating is an optical component with a regular pattern which splits light into several beams traveling in different directions. One consequence of diffraction is that sound from a loudspeaker will spread out rather than just going straight ahead. Sunglasses with polarizing films on them are used extensively while fishing and boating. These sunglasses are designed in such a way that one can look right through water. Reflection of waves of seawells or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learnt. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. The ability of an optical instrument to produce separate images of two objects very close to each other is called resolving power. The resolving power of a lens is its ability to resolve 2 points that are close to each other. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Malus' law states that when completely plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosines of angles between the transmission axis of the analyzer and the polarizer. When light falls on the interface between two transparent media, it is partially reflected and partially refracted.